So before we talk about special case factoring, I want you to go ahead and pause this video, and I want you to review some concepts. I want you to multiply these binomials and multiply these squared binomials. So pause the video and then restart it again. Okay, so hopefully you're here to check your work after you've already done it. So we are going to, and this one's especially important. Actually, both of these are interesting. If you look at this, you have the same numbers inside the binomials, but you have a plus and a minus. Same thing here. You have the same terms inside the binomials, but you have a minus and a plus. Look what happens when you multiply the pattern where it's the same thing in the binomials, but you have this plus minus pattern. We kind of talked about it yesterday. We talked about the difference of two squares. Look what happens. So if I multiply my first terms, I get x squared. And then if I multiply my outer terms, I get negative 5x. If I multiply my inner terms, I get a positive 5x. Notice how those are going to cancel. And then if I multiply my last terms, I get a negative, because I have a positive times a negative, 25. So then, when I collect like terms by adding, my positive and negative 5x cancel out, and all you're left with is an x squared minus 25. And based upon what we talked about yesterday, this is the difference of two perfect squares. Notice how its factor pattern is the square root of x squared is x and x. The square root of 25 is 5 and 5, and then you have this plus minus pattern. So then this one multiplies the same way. So first, I get 9x squared. And then outer, I get a positive 21x. And then my inner, I get a negative 21x. And then my last, positive times a negative, is a negative 49. So then when I add them together, those middle terms are going to cancel out, and I get a 9x squared minus 49. And again, you're going to notice that I have the difference of two perfect squares. 9 and x squared are perfect squares, and so is 49. Now remember, when you square a binomial, you don't just square this term and square this term. If your answer was 9x squared plus or minus 49, you missed your middle term, because this is not like this one here. If you rewrite that squared binomial, remember you get 3x minus 7 times 3x minus 7. So when you square a binomial, first, there's your 9x squared, outer, you get a negative 21x, inner, another negative 21x. Those are not going to cancel out. You don't have a plus and a minus, so they don't cancel each other out. And then last, a negative times a negative is a positive 49. 9. All right, so now when I add down, I get a 9x squared, but a negative 21 and a negative 21, when adding two numbers of the same sign, add and keep the sign, you get a negative 42x, and then plus the 49. So if you forget to write out your squared binomial correctly by rewriting it, you are going to miss that middle term. So that means that if you did this one wrong, you probably did this one wrong. So pause the video at this point if that's the case, and redo your work for this one so you get the correct answer. So again, this one's very similar to this one, except when I rewrite x plus 5 squared, I get the same binomial. I don't get a plus and a minus. So I get x plus 5 times x plus 5. So therefore, I must have a different answer. So then first, x squared, outer, 5x, inner, 5x, and last, 25. So now when I add down, I get an x squared. And then a 5 plus a 5 is 10. X plus 25. Okay? So there is a difference between multiplying a squared binomial and multiplying the same thing that has a plus minus. So let's talk about special cases, because all 4 of these are special cases. Okay, so today we're going to talk about factoring special cases. So we've already talked a little bit about factoring the difference of 2 squares. We did that in yesterday's lesson as well as in your warm-up. But here is the official factor pattern that you must know. So if you multiply 2 binomials with a plus-minus pattern where the first and last term are the same in both binomials, but you have that plus and minus, 100% of the time they will multiply out to being the first squared minus the second squared. So in theory, you should not have to FOIL it or do the vertical method or the Punnett square. As soon as you see this plus-minus pattern, you should know that it multiplies as the difference of 2 perfect squares. So you could go from here to here and show absolutely no work. So you also have to know it forwards and backwards. So in other words, if you see the difference of 2 perfect squares, you know that it factors as this plus-minus pattern. You just take the square root of a squared, which is a, and put that in the first slot. Take the square root of b squared, which is b, and put it in the second slot, and you're done. This only works for the difference of 2 squares, not the sum of 2 squares. So if this is a plus in here, this does not work at all. In fact, you cannot factor the sum of 2 squares at all. So that's what this is all about. You might want to highlight that. Beware. This process of factoring does not apply when there's that plus sign right there. So let's try some. You go ahead and pause the video. I want you to use that factor pattern. We've already worked with it a little bit, so I feel like you should be able to do this. So go ahead and use that factor pattern. Actually, maybe I'll just do the first one with you, and then you can pause the video. So as you look at number 21, you see the difference. X squared is a perfect square. Remember, if this exponent is even, 2, 4, 6, 8, then it is a perfect square. And this is also a perfect square. So as soon as I see that, I'm going to immediately put 2 binomials and a plus-minus pattern. And then all I'm going to do is take the square root of the first term, so the square root of x squared is x, and that goes in the first slot. And then I'm going to take the square root of the last term, ignore the negative, just taking the square root. Square root of 4 is 2, so 2 goes here, and a 2 goes here. And if you refoil it, you'll see that x times x is x squared, so there's the first term. Then x times negative 2 is a negative 2x. 2 times x is a positive 2x. The negative 2x and positive 2x are going to cancel each other out. And then 2 times negative 2 is a negative 4, and there's your second term. So you go ahead and pause the video and do these 3, and then restart it. Okay, so hopefully you've tried these. So for all of these, this is the difference of 2 perfect squares. So I've got my plus-minus pattern, and then the square root of y squared is y, square root of 81 is 9. And it's that simple. This one looks just a little bit more complicated because you've got 2 variables and some bigger numbers. It doesn't matter. You still have the difference of 2 perfect squares. 9 and 25 are perfect squares. We know that x squared is a perfect square, and remember this is even. So we'll talk about that one in a minute. But the square root of 9 is 3, square root of x squared is 2. So I'm going to put, or square root of x squared is x. So I'm going to put a 3x here and a 3x there. Then the square root of 25 is 5, and the square root of y squared is y to the 4th is y squared, and here's why. Because if I have y times y times y times y, that's y to the 4th, and I'm taking the square root. Remember, we're looking for groups of 2. There's 1, there's 2, so it's going to equal y times y, which is y to the 2nd. And so you don't take the square root of the exponent. What we actually do is divide that by 2 because that's the index here. So the square root of 25y to the 4th is 5y squared. So a 5y squared here and a 5y squared here. That's it, fully factored. And then the last one, so we have our plus minus pattern. The square root of m squared is m, and the square root of n squared is n. So we have an m, n. Whoops, I put that one a little close. I don't know why I did that. I'll move that one over. So I have my m and n. And the square root of 49 is 7. And 7. And that's it. Let's look at the next slide. So these ones are a little bit more complicated because right now 72 is not a perfect square. R to the 6th is, because this is even, so if we divide that by 2, we get 3. And 2 is not a perfect square. But remember, the very first question that you're really supposed to be asking yourself is, you should write this down, is there a what? GCF is correct. All right, so between 72 and 2, 2 being the smallest, since 2 divides into 72, 2 is the GCF. They do not have any R's or S's in common, so we're going to divide by 2, and we get 2 times. 72 divided by 2 is 36, and then we have the R to the 6th, minus the 2's here cancel, and so we're left with s squared. And then you have to look inside the parentheses and see, can I factor this? The only binomial you can factor, besides taking out a GCF, is the difference of 2 squares. So we have the difference. This is a perfect square. 36 is a perfect square, and so is s squared. So that means this factors into that plus minus pattern. So we have 2 plus minus. So then the square root of 36r squared, the square root of 36 is 6. And then remember, you're going to divide that exponent by 2. We don't take the square root of the exponent. We take whatever the index is, since the index is a square root, not a cube root, not a fourth root. We are going to take that index, whatever it is, in this case the square root, and divide it to the exponent. You learned that in Algebra 1. So then 6 divided by 2 is 3. So we get r to the 3rd. And if you think about it down here, let's do the square root of, I'm just going to prove to you that that works. So there's 6 r's. We want groups of 2, because it's a square root. So here's one group of 2. So then one r comes out in front. Another group of 2. So we get another r out in front. And then a third group of 2. And a third r out in front, which is r cubed. So it works. All right, so we're going to put that in both first slots. So 6r to the 3rd. And then we're going to take the square root of s squared. Easy enough, that's just s. And then you always just have to double check your binomials to make sure that they're not still factorable, to make sure you didn't forget a GCF. Or you might still have the difference of 2 squares in this minus pattern right here. All right, so pause the video. I want you to try this one on your own. So hopefully you realize that the GCF is going to be 2a squared b. So we're going to divide each of these by 2, a squared b, and 2, a squared b. And that's going to pull out in front. And then the 2's are going to cancel, the a squares are going to cancel, and the b's cancel. So as soon as that happens, remember anything divided by itself is 1, so it doesn't disappear. You should have put a 1 here. And then minus 32 divided by 2 is 16. Then remember, when we were dividing like bases, we subtract exponents. So 4 minus 2 is 2. So we get a squared. And then the b's here cancel. So that's going to cancel with that one. Then look inside here. This is the difference. 1 is a perfect square because remember, 1 times 1 is 1. So you can take the square root of 1. The square root of 1 is 1. and this, of course, is a perfect square. So we've got 2a squared b, and then this is going to factor into a plus minus pattern. So the square root of 1 is 1. And the square root of 16a squared is 4a. Now normally, okay, this is fully factored. This is the difference. This is a perfect square. 4 is a perfect square, but this a has an exponent of 1, so it is not a perfect square. So therefore, this is not the difference of two perfect squares. So this is fully factored, and this is your final answer. This is our final answer over here. So now we're going to look at perfect square trinomials, and they come from those squared binomials. So if you have a plus b squared or a minus b squared, remember this is called a squared binomial. It gives you this wonderful factor pattern here. And so instead of taking that a plus b squared and multiplying it out as a plus b times a plus b and foiling it, you could memorize the factor pattern. And notice that both of these have a middle term. So I'm going to put off here to the side, let's just do something simple, x plus 3 squared. Now remember that this is x plus 3 times x plus 3. So I'm going to prove to you that the pattern works, which is first x times x, which is x squared, then x times 3, which is positive 3x. Then we're going to distribute the 3 times x, another positive 3x, and then 3 times 3, which is a positive 9. You're like, well, this has 4 terms. Remember these middle two, they are like terms, right? So they're going to combine. There's 2 of them. So we'll finish that in a minute. But let's go back over here and look at this factor pattern, because this is the one that matches x plus 3 squared, because there's a plus here and a plus here. If this were a minus here, then we would use this one. So notice that the pattern says a being our first term, b is our second term. So you're going to take the first term and square it. First term here was a, they squared it and got a squared. Notice that our first term here is x, and if we squared it, didn't we get x squared? Then it says take 2 times a times b. So you're going to take this times this and double it. Why? Because if you take x times 3, that's 3x, and double it, didn't we have 2 inner and outer terms that were identical? That's why we have 2 of these 3 times x's. So 2 times x is 2x, times 3 is 6x. Isn't 3x plus 3x 6x? So that would become a 6x. And so that's your middle term. And then it says take the last term, and square it. That's how they got b squared. So take 3 and square it, you get 9. So we could have gone from here to here and not had any of this interim work. So if you took x and squared it, you get x squared. Then 3 times x is 3x, times 2 is 6x, and then 3 squared is 9. Done. You don't have to show any work for a perfect square binomial or a perfect square trinomial. Now the other thing I need you to start to do is to look at a trinomial and determine, is it a perfect square trinomial, so that you could go from here and factor it like this. So for instance, if I notice, if I took the square root of the bookends, so the bookends are the first and the very last term. So if I took the square root of this, I'd have x, and the square root of this, I'd have 3. So x times 3 is 3x, and then double it is 6x. Then I could say, oh, this is a perfect square trinomial, and I know that its factor pattern is 1 set of parentheses squared. So then all you have to do is take the square root of the bookends, square root of x squared is x, square root of 9 is 3. Of course, you could still use the method that I taught you before, which is just to read it backwards, what factors of 9 add to give you 6x, and you could do the t-chart, but that's going to take you longer. And then you might be asked to determine, is this a perfect square trinomial or not? So you need to be able to apply the test for this middle term. And so this is just an explanation down here of what we just went through. So this is the square. A squared is the square of the first term of the binomial. There's that first term. 2ab is twice the product of the first and last terms, right? So a times b times 2, because you've got 2 of them. And then this is just the square of the last term, square of this. All right, so let's go ahead and try that. So for example 1, let's just determine first, is there a GCF? Well, as soon as you have a 1 here, there's no numbers that are GCF, and then they don't have any x's in common. So as soon as I see that my first term is a perfect square, x squared is a perfect square, and my last term is, and mind you, this has got to be a positive. If this is a negative, there is no number times itself that gives you a negative. You either have a positive 6 times a positive 6 gives you a positive 36, or a negative 6 times a negative 6 gives you a positive 36. There is no way to take a positive 6 and a negative 6, which are two different numbers. Do you see what I'm saying? So if we took the square root of this, it would either come out to be 6 or negative 6. So this last term has to be positive. All right, so I recognize that my bookends are perfect squares. Now I have to do the test to determine is 12x the match for this perfect square trinomial. So remember, your test is 2 times a times b. And I would like to see you write that down. So I've got 2 times, and then to find out what a is, you take the square root of the first bookend, which is x, and then to find b, you take the square root of the last term, which is 6. So then multiply these together. 2 times x times 6 indeed does match 12x. So as soon as you see that it matches, then you can immediately say, oh, this just factors as one set of parentheses squared. And then when you factor this, something from each of these terms helps you in the factoring. So for instance, the first term is going to give you the first term here. So the square root of the first term, which is x, goes here. Then the middle term contributes its sign. If the middle term is positive, you'll have a plus here. If the middle term is negative, you'll have a minus here. So because our middle term is positive, we are going to put a plus in the middle. And then we get this last term by taking the square root of the last term. So the square root of 36 we said was 6. Whoops, that was supposed to be green. So 6. So as you can see, all 3 terms contribute something inside here. First term contributes this, middle term contributes the sign, the last term contributed this. And then that's it. Technically there's no work other than to determine, I mean, it's not enough, let me move that 2 down to here. It's not enough to just say, oh, these are perfect squares. You have to test that middle term, because what if the middle term had been 6x? Then it would not have matched this 2ab. It would have just been ab. So you have to be really careful and make sure that that middle term matches. So I want you to go ahead and pause the video, and I want you to apply the test for the middle term and see, is negative 6a the correct middle term when 9a squared and 1 are your first and last terms. So pause the video and apply that test. Okay, so let's go ahead and write out our 2, it's supposed to be red, 2 times a times b. So we have 2 times, our a is going to be the square root of 9a squared, which is 3a, and our b is going to be the square root of 1. So then we're going to multiply it all together. 2 times 3a is 6a, times 1 is 6a. Don't let the sign bother you. It doesn't really matter what the sign is. We don't care about the sign. So 6a matches. So yay, it matches. So then immediately you can factor this as a set of parentheses squared. And then we're going to put in our values. I know that the middle term is negative, so a negative is going to go in the middle. And then the square root of the first term here goes here. We've already figured these things out down here, right? So the square root of 9a squared goes here, which is 3a. And then the square root of 1 goes here, which is 1. And then that's it. This is our final answer. And that's all there is. So now you have homework to do. Just text us with any questions. Have a good day.